Hello everyone, I'm Josh, and today I want to walk you through how to set up a scattering simulation using Lumerical's FDTD software. So, first of all, I want to talk about the scattering problem. So, what the scattering problem looks a little something like this. We have an instant plane wave coming in into some sort of nanoparticle, let's say, and the plane wave is going to scatter from that particle. So what we want to know is how much of that light was scattered and how much of that light was absorbed by the particle. And this is what is very commonly done in nanophotonics and plasmonics simulations. So now the question is, how do we do such a problem using FDTD? And that is the goal of this presentation. So first thing we want to do is to create a simulation region. All right, so, well, before we do that, we need to open up the FDTD software. So let's open up Lumerical software. At this point, I'm assuming you already have it downloaded and you have a license. Okay, what's that? All right, so the first thing we're going to do is we're going to click on the simulation icon. Once we click on this icon, we're going to be able to edit all of these different simulation parameters. So we get to choose if the simulation is 2D or 3D. We get to set the simulation time, the temperature in the simulation, the background material, the domain size, the step size, the boundary conditions, and all that fun stuff. And for a scattering problem, our boundary conditions are going to be PMLs on all sides of the simulation domain. So let me walk you through that quickly. So first thing we actually want to do before we do that is we want to go into settings, into length units, and naturally they set the length units as microns. Now, I'm a nanophotonics guy, so I like nanometers. Next, as I said, we click on the simulation box, which is just this orange box up here, and we right click, and we click Edit Object. So right away we can see here that the default is a 3D simulation, but if you want to go with 2D, you can click on that. But for now, we're going to stick with 3D. The simulation time, they set it to 1000 femtoseconds. That's pretty decent. The simulation temperature, we don't usually have to worry about that in our sorts of simulations. If you're doing some high intensity laser pulses, then yeah, you could expect that the temperature is going to change, so maybe you want to play with that then, but for now we're going to ignore it. And the background material. So they assume the background is a dielectric with an index of 1, so that's just vacuum. But let's say if your background is glass, then maybe you want to go with 1.5. If it's water, then 1.3. But for now, we're going to stick with vacuum, and we're going to keep the index at 1. You can also define the background as any one of these materials that they have built in. So that's quite nice. The geometry. So now we're going to set how big the simulation domain is going to be. Again, we're going to deal with a nanoparticle. So our particle is going to be on the orders of tens of nanometers. So we're going to create our simulation domain to be a 200 nanometer by 200 nanometer by 200 nanometer cube. So 200, 200, 200. And let's go back to edit object here. Sorry. So as you can see, that our minimum x is at negative 100 nanometers, our maximum x is at 100 nanometers, and it's the same for y and z. Also, I recommend centering your simulation domain at 0, 0, 0. A lot of the times when you open up this software, the default is some crazy decimal place number. I don't know why they do that, but 0, 0, 0 is what I always choose. Mesh settings, so if you just leave the mesh settings alone, the software will actually set up the FDTD mesh for you. Now, I'm a fan of the uniform mesh because that's what I use in my own custom software usually. So I click on uniform, and that way I know what the step size in the simulation is. So I am choosing 2.5 nanometers for the step size in the X, Y, and Z direction, which means that our simulation domain is actually going to be 80 by 80 by 80 Yee cells. That's just 200 divided by 2.5. The boundary conditions are PMLs. They are all going to be PMLs. If you're doing, so that's for a scattering problem, you can usually be using PML boundary conditions. However, if you're simulating, let's say, a metasurface or something that's periodic, then you want to use periodic boundary conditions. If there's some sort of symmetry in your simulation, so let's say if you're simulating a scattering from a sphere, then you can use symmetric and anti-symmetric boundary conditions. If you're doing a periodic simulation, but with a plane wave at an angle, then you're going to want to use block boundary conditions. But for now, we're sticking with PMLs. And the advanced options, you shouldn't have to touch this. So what Lumerical actually does is they will shut off your simulation once the electric fields reach a certain value. So that's what this is. If the electric fields reach 10 to the negative 5, then it's going to cut off your simulation domain, which is, sorry, it's going to cut off your simulation. And that's completely fine. I would leave that. All of this stuff I wouldn't touch. Okay. So now I'm going to click on this magnifying glass to recenter everything. And here's your simulation domain. So we have a big empty space, and these orange regions here are your PMLs. And now I should talk about these viewing windows. So this top left-hand viewing window is the XY view. We have the XZ view. We have the YZ view, and then we have a 3D render. For some reason, it doesn't actually show a cube. It shows a rectangular prism, but the domain is cubic, as you have seen. If you want to see what the actual mesh looks like, you can click on this icon down here on the left-hand side. If you click on that, then we can actually see the Yee cells in this simulation. All right, so there are going to be 80 Yee cells in each direction. Okay. Next, we need to add a source. So FDTD offers you a wide range of sources. For a scattering problem, we want to use a plane wave source. If you have PMLs in all directions, which is what we have, then you need to use a total field scatter field source. And I'll talk about that in a second. If your simulation domain is periodic, so if you're doing metasurfaces or gratings or anything like that, then you need to use a plane wave source. And if you're using waveguides, then you want to use a mode source. I believe they also have other source options. So I'm going to go into here. Oh, there's also the dipole sources. So that's useful if you want to do calculations of fluorescence enhancement. The Gaussian beam is if you're doing any sort of it's any sort of focus beam simulation. Import, I don't know what that is. I think that's you're allowed to design your own pulse shape. And global property, I don't know what global properties are. I never used that. So I'm going to click on total field, scatter field. And they set up the geometry terribly right off the bat, so you got to go in and edit it yourself. So again, reject changes. You can right click, edit object. And so the injection axis, so that's what direction that the pulse is going in. So I'm actually going to set the injection axis to be the x-axis. So I want the pulse to be traveling from left to right. So yeah, it's forward. The amplitude, the phase, the angle, and the polarization angle. So these are all things you can play with. So if you want the pulse to come in, instead of from left to right, you want to come in diagonally, then you can set the angles to your heart's content. The geometry, again, center everything at 0. All right, and we want the total field scatter field to also be cubic to match the simulation domain, and we need it to be smaller than the simulation domain. So I'm going to make it a 160 by 160 by 160 box. All right, next we go into the frequency and wavelengths. So I'm interested in plasmonics, and I like silver. So silver has a lot of its interesting plasmonic properties between 200 nanometers and 500 nanometers. So I'm actually going to set the minimum wavelength to be 200 nanometers. So what this is going to, let's go back. What this is going to do is it's going to make the pulse properties so that the wavelength range of our pulse, of our source, is going to be between 200 nanometers and 700 nanometers. And of course, there's a bit of a tail off into the infrared over here, but that's okay. And they show you what the time domain version of the pulse looks like, and it's so small because it's very broadband. Now something else that you may want to do, and okay, no, you don't do it here. Never mind. But this is where you set the frequency range that you want to analyze. So because FDTD is a broadband simulation and it's time domain, a lot of the properties you're going to want are frequency domain. So if you want to analyze frequency domain data, you need to go into the source and set what ranges of wavelengths or frequency you want to analyze. So I'm going to click apply and OK. Alright, so now we have our simulation domain set up with boundary conditions and a source. Okay. Right, as I mentioned, if you have PMLs, you use a total field scatter field. Now we can run an actual simulation. So first thing I'm going to do is I'm going to add a movie monitor so we can actually see the electric field in time. And this monitor can be bigger than the domain, so I'll show you what that means. Next, we're going to click run and save the simulation, and we're going to watch the movie after. Alright, so let's add in the movie monitor. So you go up to monitors, click the arrow, and add movie. And you can see here that naturally it just makes the monitor big. And we're going to actually keep it big, because what's going to happen is that the simulation is going to be like, all right, well, this part of the movie monitor is outside the simulation domain, so they're going to clip it to be just inside the simulation domain. So you don't have to worry about remaking the size of this. Now we're going to click run. And it's going to ask me to save this, so I'm going to save this as lesson scattering. All right, save. And now it's running the simulation. So what you're going to see here is it's going to approximate the simulation to be 33 minutes long. It's not actually going to be 33 minutes long because the simulation domain is empty. It's actually going to be quite fast. So we'll see if I have to pause the video at any point here. But oh, nope, it's done. All right, so now if you right-click on the monitor, you can click play. All right, so it went to my other window, so I'm going to just transfer this over here so you can actually see it. If you're using Windows, I'd recommend using the Windows Media Player. For some reason, Lumerical's video files don't like a lot of media players, so this one works. So if you click play, then what you see is you see the pulse going by. So I'm going to repeat that one more time. So let's go into the middle here. So it's a very short pulse because it's very broadband. There's a lot of frequency components in it. It covers the entire visible range. And what you can actually see here is you can see the work of the total field scatter field source. So this region here inside this box is called the total field range. So that is where the electric field gets injected. And you can see here in the scatter field, there is no electric field. Now, if we place some sort of object in the middle here to scatter the light, then there's going to be light in the scatter field region. So in this region, we can actually measure the light that is scattered. The only light that will enter this region is something that is scattered. Since we have no scattering, then there's no light in this region. I've said that multiple times now. I hope it's hammered in. Great. All right, now we need to add a particle or a scatter. So what we need to do is we need to go back into layout mode. So right now we're in analysis mode. So that's because we just ran a simulation. So we need to go back to layout mode by clicking this icon. We need to click on structures, and we can add any shape that we want. We need to make sure that it fits in the simulation domain, so we need to edit the geometry. We need to pick a material for the structure, and then we need to rotate the structure if we need to. And then we're going to click run, and again, watch the movie, because that's the fun of time domain simulations. So click on layout, click on structures, and now you can add any of these sorts of pre-made shapes, or you can combine shapes to make new shapes. But I'm going to go with a sphere because I'm a physicist and I'm boring like that. So I'm going to right click on the sphere and click edit object, so you can see the sphere is outside the simulation domain, so that's no good. Again, I don't know why they don't just set everything to 0, 0, 0, because that's what we all end up doing anyway. I'm going to set the radius to be 50 nanometers, so it actually fits in the simulation domain. Alright, so let me just show you what that looks like. There we go, now it's centered in the domain. So what you're going to want is you're going to want to put your shape, again, it doesn't have to be a sphere, it can be anything that you choose, but you want it to be small enough that it's several cells away from the total field scatter field boundary. So you don't want the sphere to be too close to this boundary. You want some space. Now I would argue you want even more space than this, and that's the downside of using a commercial software like Lumerical that runs on your laptop or desktop computer, is that you're restricted in memory. So that's why a lot of people who do professional FDTD simulations use supercomputers. But because we're restricted in memory, we need to make do with this. So this sort of spacing between the total field scatter field region and the sphere, it'll work. So now we need to edit the material. So right now the material is just set as a dielectric with an index of 1.4. So I guess that's some sort of glass. Now, because I'm interested in plasmonics, I actually want to go with either silver or gold. So one of the first things you'll see here is silver, and there's different models for silver. So there's the CRC model, there's Johnson and Christie, which is what I'm actually going to use because that's one of the most common models for silver there is. There's also Pallic, and you can see for Pallic, this one, it's valid for wavelengths between 0 and 2 microns. And there's another one from 1 to 10 microns. Again, I'm going with Johnson and Christie because this is what works for the visible wavelength range. But yeah, there's a whole bunch of materials you can play with here, but I'm going with silver. Rotations, now you can click on, you can rotate your object. For a sphere, there's no point in doing that because it's already spherically symmetric. So, and then there's graphical rendering, which is just, you know, it just is how you see it in the display window, so don't even worry about that. Alright, let's click apply, and okay, so now you can see that our particle is silver. Alright, so I still have the mesh turned on here, so you can still see the meshing. And if we zoom in here, you can see that there's that the boundaries of this sphere are actually going to be very blocky, right? Because it either exists in this square or it doesn't. So that's and we're going to see that actually when we play the video of this simulation. So let me just click run here. Now, because we've added a material in, this simulation is going to be quite a bit longer, though it won't be more than a few minutes, so I'm just going to sit here and wait for it to finish. Again, I guess it's going to be 30 minutes. Lumerical software is not very good at guessing the time of their simulations. So if it says 30 minutes here, it's probably going to be 1 minute or 2 minutes. And here you can see the auto shut-off level, so you can see that this number is going to decrease, and once it reaches 10 to the negative 5, the simulation is going to stop because the electric field has pretty much diminished. And according to this, we're only 1% for the simulation, but again, that's a lie. And it's done. So that took about 20 seconds. So now we're going to watch the movie of the simulation, so I'm going to click play. And there you go. So what you just witnessed is you witnessed a plane wave that we saw in the previous movie, incident on a silver sphere. So let's kind of look at what actually is happening here. So remember, our sphere has a diameter of 100 nanometers. So when the plane wave hits the sphere, some of the electric field is actually going to enter the sphere, and it's going to decay within the skin depth, which for silver I think is on the order of tens of nanometers. And inside the center of the sphere, we're generally going to see very little electric field in the center of the sphere because it's a metal, it's a conductor. Electric field is not supposed to penetrate it very much. And what we also see is that around the sphere, which again Lumerical highlights quite nicely for us here, it's very blocky. We get all this gross, spurious electric fields. So these are not physical. These electric fields that you see here, these peaks, are due to the fact that that the side of the sphere is blocky because of the Yee cell. So the smaller the grid size of your simulation, the more accurate your simulation is actually going to be. So 2.5 nanometers is actually not very good. Again, you see this like interference happening here. That's not supposed to happen. That's not physical. So yeah, just keep that in mind. Again, this is why we use supercomputers, so we're not restricted by these very large grid size. Oh yeah, also because now we have an object in here, we have some electric field in the scatter field. So if we were to kind of like place some sort of monitor here, we can actually calculate the electric field that's being scattered, which is again the goal of this video. Alright, so next up we want to add a monitor, as I said. So we're going to add a frequency domain monitor. And then again, like the movie monitor, this is going to be bigger than the simulation domain, and that's okay. And what this monitor does is it's going to take a Fourier transform of the time domain fields. So at each time step of the simulation, it's actually going to, it's going to be integrating the time domain electric field to the frequency domain. So this integral is actually going to be approximated by a sum where you just add the electric field at each time step. And it also calculates the electromagnetic intensity, which is just the time average Poynting vector, which is done at the end of the simulation. So it knows what E at omega is from this Fourier transform. It's going to know what H, what the magnetic field of omega is. And then it just does this calculation, and it'll give you the intensity or the power of the simulation. So I'm going to go back and I'm going to add in that frequency domain monitor. So again, first of all, we just click layout mode, we click on monitors, and we click on this frequency domain field and power monitor. There's also this frequency domain field profile, which I don't quite know the difference between these two. I'm sure there's like a slight difference, but they both pretty much do the same thing. So just click on this one. And again, it's bigger than the simulation domain, and that's okay. This software is smart enough to know to clip that. But what we do want to do is we got to go in here and edit it. So simulation type, you can tell it if it's 3D or 2D. Go into the geometry again. We don't really need to play with that. Data to record. So what it's going to do is it's going to calculate the frequency domain electric field EX, EY, Z, and the magnetic field HX, HY, HZ, and it's going to calculate the power, which is just the Poynting vector but scaled in some way. Spectral averaging, so I wouldn't touch that. You don't really need to touch any of this. But what you do want to do is you want to go back to General, click on Set Global Monitor Settings. Alright, so when we set up the source, we already said that we wanted wavelengths between 200 and 700 nanometers. And now we want to tell it how many frequency points do we want to calculate. So right now it's set to 5. So if we were just to run this simulation, we would only be able to see the electric field at 5 different wavelengths between 200 and 700 nanometers. That's usually not good enough, especially if you want to plot some sort of spectrum. So I'm going to say 21. I would say stick with odd numbers as a general rule. That's useful more when you have some sort of Gaussian pulse where you want to have that center frequency well defined. Anyway, I always go with odd numbers. So 21. Apply. Okay. Okay. And again, we're just going to run the simulation as it is right now. So now because we are now doing some sort of Fourier transform, it's going to take a bit longer for the simulation to run. The more frequency points you choose, the longer it's going to run, because it is an additional calculation that it is doing on the side. But it's still going to run pretty fast because we're using a rather large step size. Okay, so now the simulation has finished running. So what we're going to do is we're going to right-click on the DFT monitor. We're going to click Visualize. And so what you can see is we can actually look at the frequency domain electric field, so E, the magnetic field H. We can look at the power, which is just the time average Poynting vector, so that's P. And then there's also a spectrum. So T is actually going to be a line plot, and that kind of integrates the power over the area that it's doing the Fourier transform. So if I click on that, let's see. Yeah, so you get this spectrum-esque kind of thing. It's really messy though, so it's not really telling you much. So what I'm going to do though is I'm going to click on Visualize, and we're going to visualize just the electric field. Okay, make that bigger. And we get this. So Lumerical has this weird bug where it draws things in a very weird way initially. So if you just click on Redraw over here to the right, there you go. Now we can actually see what the electric field looks like. So this tells you the electric field. This shows you the electric field at a single wavelength component. And that, if you click down here, you can see that that is 700 nanometers. All right, so we can see that the electric field almost looks dipolar, right? And that's actually what it's supposed to look like. Because the wavelength component, 700 nanometers, is much bigger than the sphere's size, which is 100 nanometer diameter. Okay, so maybe it's not much bigger, but it's big enough that the sphere kind of acts like a dipole in this field. And what you're going to see is as we decrease the wavelength, or as we make the wavelength smaller relative to the sphere size, this dipolar behavior actually will go away because we can no longer treat the particle as a pure dipole. What you can also see are the enhanced near fields. So the cool thing about these metallic spheres is that they enhance the electric field around them. So here you can see that the electric field is about 4 times bigger at the surface of the sphere. So that's why people like these plasmonic particles, these gold and silver particles, is that they actually make the electric field stronger around them. So if you put, let's say, a fluorophore, some sort of fluorescent molecule, right beside the sphere, then that fluorophore is more likely to absorb a photon and excite to a higher energy level. We can also use plasmonic particles to enhance the behavior of quantum dots, right? Again, if you put a quantum dot beside this particle, the quantum dot is more likely to absorb photons because there's a higher electric field intensity around the edge of this particle. Okay, so now let's kind of scan through the wavelengths. So you can do that again. Make sure you're clicked on lambda. And now we click up. So by clicking up, you are increasing the frequency or decreasing the wavelength, which is actually what we're seeing here. So we're going to just keep clicking up. So we have 21 wavelength / frequency components. And we're going to just keep on clicking these, clicking these, clicking these. And you can see that the behavior changes significantly as we get into the lower wavelengths. All right. And the reason for this is that the wavelength is now becoming more and more comparable to the size of the particle, so it's no longer acting like a pure dipole. What's also happening is we're actually reaching the scattering resonance of this nanoparticle. So if we kind of go back here, all right, let's look at the scattered field. All right, so that's the region of where the electric field is lower. So it's going to be the only field in this region around the outside is the field that is scattered from the particle. Now if we go down, we actually see that the scatter field increases in these lower wavelengths. So we get a scattering resonance. And we actually expect that for a 50 nanometer silver particle, we expect that to be around 300 nanometers. In the next part of this tutorial, I'll actually show you how to calculate the scattering and absorption spectra from this particle. This video already is too long, so I'm going to cut it off shortly. But yeah, this is what the frequency domain electric fields look like. And it's always nice to look at this so you can actually see why we use plasmonic particles. Oh, over here you can see that the electric field is, so this is at 400 nanometers. Yeah, so around 400 nanometers, 430 nanometers, we get that the electric field is almost 8 times more 8 times larger than the electric field that we actually sent in. So that's what plasmonic particles do. They enhance the electric field that we sent in. So yeah, that's the time domain electric field. And I'm going to cut off the tutorial here so that next time I'm going to show you how to actually calculate the amount of power that was absorbed and the amount of power that was scattered. But for now, you've played around and we've seen enough that you can actually play around with Lumerical yourself. And I'm going to kind of give you a bit of a hint on how to calculate the scattered and absorbed power. And it actually comes, you could actually do it by using these frequency domain and power monitors in a creative way. But Lumerical actually does it for you. So if you go into analysis and click on let's see, I think it's under more choices. You can actually, let's see, where does it exist? Anywhere in here. Whoa. I actually haven't explored all of this yet, so this is kind of, oh, here we go. Cross section. So this is a bit of a hint, but this is kind of the power monitor you want to use. So I would kind of encourage you to figure it out for yourself how to calculate the scattering and absorption before just using what Lumerical gives you. Anyway, thank you very much for watching / listening, and feel free to leave any questions in the comments and I will try to answer as many as I can. Thank you very much. Bye.